Hello, human geographers, and welcome to our first lecture for our course, AP Human Geography. So let's start out by just talking about what human geography is. It's everything that we as humans do. It's where we live, where we're moving, the kind of activities that we engage in, the kind of food that we eat, the way that we protect our territory, all the different ways that we as humans interact. That's what we're going to be looking at this year. But we're going to start by talking about what it means to think geographically, or, in other words, the spatial perspective. In human geography, we're going to be looking at where all sorts of things happen spatially. And in fact, those words, spatial and geographic, are really just synonyms of each other. So when we say, where's that happening geographically, we could also say, where is that happening spatially? So we're going to be looking at where things are located in space. And we don't necessarily mean outer space, though that is a type of space. We're going to look at where it's happening geographically, where it's happening spatially, and then we're going to ask why. Why is it there? In fact, the most common questions that will pop up during our lessons will be where, why, and so what? So we'll look at where something is happening. Is that activity happening anywhere else? What do those places have in common? And then we'll ask, why is it there? Why is it in those places? Why isn't it somewhere else? And then we ask, so what? Why does this matter? How does this impact someone's day-to-day life? How does this impact my day-to-day life? And that so what question can be really important because we only have a certain amount of time and we have so many different things that we're going to look at and discuss. We got to make sure that what we're talking about really matters. And so when we talk about where things are and why they're there and the connections that they have, this chart offers us a really good way to analyze the spatial arrangement of places and phenomena, how they're laid out, how they're organized and arranged on the earth, and how that might manifest itself on the landscape both now and over time. So as we evaluate the location, position, or where something or someone is, we're talking about thinking spatially. And there's different types of ways to think spatially. You can think in space, you can think about space, or you can think with space. And so let's give some examples so we know what we're talking about. Have you ever walked through your room with the lights off and you can navigate it perfectly without tripping or falling? That's because you're comfortable in that space, your life space. And so setting the table, playing sports, giving directions, those are examples of thinking in space. Okay? When you walk down the hallway and you're able to not bump into people, that's navigating life space, in space. Now, what about space? Thinking about space, whether we're talking physical space or social space, deals with those concepts that are very big, but no less important to our day-to-day lives. How do you decide what to wear each day? You think about the climate of the region you live in and the weather of your local area. That's physical space. Then when we're talking about social space, think about when you walk onto a school campus, when you walk into our high school, where do you sit for lunch? Now, you might be starting to think about just about any movie that you've ever seen that deals with high school and all the cliches, right? All the jocks eat together. The plastics stick together. The skaters sit at the same table even if one of them secretly wants to play the cello. And of course, Gryffindors and Slytherins don't sit at the same table. That mental map that we have of our space, that's social space. That's thinking about space. And anytime that you use a chart, a graph, a diagram, a pattern, the periodic table, a concept map, a flow chart, you play chess. You're thinking with space. Now, in the 1980s, National Geographic and the National Geographic Society created the 5 themes of geography to try and better organize our understanding of geographic or spatial concepts. So these are the 5 themes: location, place, human environment interaction, movement, and region. And we're going to organize this first unit about thinking geographically, thinking spatially. We're going to organize all of our content within these 5 themes of geography. And the first few lectures are going to be about location. Location is the geographic position of people and things on the Earth's surface. And the first tool that we have to talk about with regards to geographic positioning in space are maps. So here's a quote by Arthur Robinson, a cartographer. "Some things are very small, and we must use complex electric and optical means to enlarge them so as to understand their configuration and structural relationships. We call those things microscopes. They enlarge it." All right? In contrast, geographical things are so extensive that we must somehow reduce them to bring them into view. Let's look at that map at the bottom. It's a map of ethanol plants. We can't see every ethanol plant in the United States with our bare eyes. So we need a way to reduce them, as Dr. Robinson says, so that we can study them. Because once we can see them, then we can study them. So in the same way that a microscope enlarges something that is too small so that we can study it, a macroscope reduces things that are too big so that we can study them. Maps are the macroscope. And Dr. Robinson was a cartographer, meaning that he studied and practiced cartography. That is, the art and science of making maps, including data compilation, layout, and design, and is also concerned with the interpretation of mapped patterns. So let me ask, what are the key words in that definition? You've probably heard it before today. It's probably not a new word for you. But if you needed to boil it down to 1 or 2 key words or phrases, what would they be? Maybe you said making maps. If you remember nothing else about cartography except making maps, you're probably going to be able to write a pretty good definition of that vocabulary term if you were asked to on the AP exam. That's what we want to do with vocabulary in this class. You don't need to memorize every word of these definitions, but rather come up with a couple of words or phrases that get to the core of what that term means. So since making maps are going to be our core of cartography, let's define map. A map is a 2-dimensional or flat representation of Earth's surface or a portion of it. And there are 2 major categories of maps. There are reference maps and thematic maps. Reference maps show locations of places and geographic features, but they have no analysis or interpretation. These can include physical maps, political maps, road maps, or plat maps, which show property lines. This reference map actually shows some physical features like mountains, political divisions with our states shown on them, as well as major highways. Thematic maps tell stories. And that's the most important note for this slide. Thematic maps tell stories. Typically, by showing the degree of some attribute, like you see here, or the movement of a geographic phenomenon. And in the same way that different authors can tell their stories through books or television or radio or other mediums, there are several different ways for geographers and cartographers to tell their story with thematic maps. There are choropleth maps, which is what you see here. There are dot distribution maps, which you saw on the ethanol map on the last slide, as well as graduated symbol maps, isoline maps, and cartograms. Now, don't worry, we're going to get into detail on each of those in the next lecture. But for a moment, what story do you think this map of the Human Development Index is trying to tell? Jot down some guesses in your notes. What is the story you think it's trying to tell? That is a skill that we will need to practice for the entire year. As geographers, we need to try and decipher the story behind any thematic map. And Dora helped us with that. And when geographers study the spatial perspective, where things are in space, remember, we're looking for relationships in space. And these can include things like the location of things and places, distance between, directions, orientation, patterns, as well as interconnectedness. And so we need some tools to help us with that. In addition to maps, there are other tools that geographers use when it comes to analyzing things in space. You're probably already familiar with a globe, a smaller representation of the Earth. But perhaps more important for us will be projections, which are the system that is used to transfer locations from Earth's surface to a flat map. And because the Earth is roughly spherical, there is more than one way to project the Earth's surface onto a two-dimensional or flat map. So let's start with some general classes of map projections. Conic projections take a flat map and turn it into a cone around the Earth. Cylindrical projections, you probably guessed, puts a flat map around the Earth as a cylinder. And planar projections, which are called azimuthal projections in the cartography world, connect the flat map to the Earth at a single point and extend the rest of the world out onto a plane. And there are so many different kinds of projections because there isn't one way to project the round Earth onto a flat map. Because of that, each of these projections have inaccuracies, imperfections, and we call these inaccuracies distortions. So, how can you identify these distortions? Well, the first thing you're going to want to do is start by finding the focal point of the map. That focal point might be an actual point, or it could be a line, more often of latitude, but it could be of longitude as well. So now that we've covered some general characteristics, let's dive in to some specific examples. There are a number of map projections that you will want to know by name and by visual. Some are very common on the AP exam, like the Robinson projection and the Mercator projection. Others are famous for their attempts to address certain issues, correct certain distortions of more famous projections. These include projections like the Goode's Homolosine projection and the Gall-Peters projection. But in reality, there really are an almost infinite number of map projections. But why are there so many? Because again, it is impossible to take a curved object like our Earth and put it onto a flat surface perfectly. So again, those imperfections from the projection are called distortions. And every map has them in some way, shape, or form. Every flat map is wrong. So let's take a look at them. These distortions, these inaccuracies or imperfections caused by putting a roughly spherical Earth onto a flat map are the four types that you see here. And each of these types have synonyms that you're going to want to be familiar with. Because here's what the College Board loves to do. All of our multiple choices in AP Human Geography have 5 options. All multiple choice questions have 5 options, A through E. So if they asked you, what type of distortion is most prominent on a Mercator projection, there are only 4 possible choices. You see them right there. But they have to provide 5. So they might say shape, size, distance, direction, and proximity. But you, the ever clever AP student, would realize that the correct answer cannot be distance because proximity means the exact same thing. And if that were right, they would both have to be equally correct. And therefore, they must both be equally wrong. So now you've increased your odds of getting this question correct from 1 in 5, or 20%, to 1 in 3, or 33%. You eliminate one more, now we're talking a 50-50. All right? So those 4 types of distortions that we've been referring to are shape or angle, size or area, and notice that the 2 S distortions, shape and size, have synonyms that both start with A, angle and area. That's one way that I remember them. Then you have distance or proximity, and you have direction. Sometimes this is referred to as compass bearing. Now, in general, the larger the area of Earth that is depicted on a map, what we will later call smaller cartographic scale, the greater the distortion that is built into the map. So a small area will have distortion that is less noticeable. But remember, it is a flat projection of something that is round. So it does still have inaccuracies, even if you can't necessarily see them. So now let's talk about each distortion in turn. And for each distortion, we're going to discuss what it means, and we'll provide a map that has no distortion of that kind. So let's look at this slide for an example. Distortion of shape means that the angles are distorted. So land masses will typically look more stretched out or smushed. I guess the technical terms would be elongated and squat, but I like to say stretched and smushed. And so this Lambert conformal conic projection displays shape exactly as you would see it on a globe or the Earth itself. It has perfect shape. In fact, that's what conformal means, is that it preserves shape, but in this case, distorts size. So if we did a pros and cons list for the Lambert conformal conic projection, we'd say pro is shape. It's preserved. It's perfect. Con, size. I mean, look at Australia. It looks bigger than the US and Canada combined. It distorts size. So, speaking of size distortion, that means that land area is distorted. So land masses look bigger or smaller than they are in reality. So let's look at the Gall-Peters equal area projection. In fact, in its name of the projection, it says equal area. Size is accurate. Area is equal. But look at the shapes. Someone sat on Greenland. It's smushed. And land masses near the equator are all stretched out, like Africa and South America. But we know that would be the issue because there's pros and cons. On the positive side, the pros, size is accurate. Greenland is about 1/14 the size of Africa. It's 14 times smaller than Africa. This projection is accurate with that. On the negatives, Greenland's smushed. Now, the distortion of distance or proximity. Now, proximity just means how close two things are to one another. So in this case, we're talking how close land masses are to one another. So a distortion of distance means that distance has been increased or decreased. Now, this is an azimuthal equidistant projection. So equidistant is in the title, and that means that distance is consistent from the focal point. And since it is an azimuthal or planar projection, that means that it is connected at the Earth at just a single point, the focal point. Can you tell what that focal point is? It's the North Pole. So everything is the correct distance from that focal point. Everything is equidistant from the North Pole. But remember, we said that distortions happen farthest from the focal point. So take a look farthest from the focal point, and you'll notice that that's where the distortion is the greatest. Antarctica completely surrounds the world. This projection distorts the size and shape of Antarctica, along with other land masses, in an attempt to preserve distance, specifically distance from the North Pole. Distortions of direction mean that the direction from one area to another is inconsistent. The Mercator projection has perfect direction, or what you'll often hear is a line of constant compass bearing. This projection has a line of constant compass bearing. Okay? This is done by maintaining perfect right angles at lines of latitude and longitude. But those perfect right angles severely distort the size of land masses. Look at Greenland. It's the same size as Africa. But we just said that Africa is 14 times bigger. So this is some severe distortion of size and even of shape far away from the focal point. The focal point in this case is a line of latitude, the equator. So the farther you get away from that, the extreme poles, extreme north and south, that is where distortion is greatest. But direction is perfect. So now let's look at a couple specific projections, okay? Some of which we've already talked about, but we want to make sure we're familiar. So the Mercator projection is a representation of a sphere where lines of latitude and longitude are straight and at right angles to one another. And so that makes this projection ideal for navigation. It was created in the 1500s by a cartographer, Gerardus Mercator, in an attempt to help people navigate the oceans. It distorts land area and, to a certain extent, the shape of land masses, especially at higher latitudes. And there's different ways that we could say that. High latitudes, near the poles, extreme north or south, however you want to describe it. But it does that for the sake of preserving direction. So let's do some pros and cons. Positive, direction, constant compass bearing. On the negatives, size is certainly distorted, especially at the poles, and to a certain extent, shape. The Gall-Peters is another one that we've looked at. It has perfect size. It's equal area. That's what cartographers will call it. But it distorts shape to accomplish that. Remember, someone sat on Greenland. Positives, size or area. Negatives, shape. Now, the Goode-Homolosine projection is one that we haven't looked at in detail yet. Now, this one kind of looks like someone peeled an orange and then drew the world on it. In fact, there are some human geo teachers that have their students do that in class. Now, this map is also an equal area map, meaning that size is accurate, but with less distortion of shape than we saw with the Gall-Peters. It does this through its interruptions. While these interruptions are intended to preserve the size of land masses, as well as provide a more accurate shape than we see in the Gall-Peters, it doesn't do that for all land masses. Greenland is in 2 pieces! Actually, one of my former students thought that that would be an awesome name for a band. Greenland in 2 pieces. Like, oh man, how did you get tickets to Greenland in 2 pieces? I'm so jealous. I don't know. Awesome rock names aside, let's talk about some of the positives and negatives. Positives for this projection, it has equal area and generally has better shape than the Gall-Peters. But on the negatives, it has distortion of direction and distance, as well as shape further from the focal point. And it's interrupted, which can be a positive or negative. It accomplishes some of its positives, but also creates some of its negatives. And as a final note, the choice of map projection often depends on what the cartographer is seeking to accomplish, the story they're seeking to tell. The Goode-Homolosine projection interrupts bodies of water, generally, to maintain land masses, generally. But what if you wanted to study the oceans? A different projection might be more useful for that. Finally, we have the Robinson projection. We mentioned just a second ago that the choice of projection depends on what the cartographer is seeking to accomplish. Well, Dr. Arthur Robinson, the cartographer we quoted at the beginning of this lecture, wanted a balanced approach. In fact, this projection was used by National Geographic beginning in 1988 when it replaced the Van der Grinten projection. And then the Robinson projection was in turn replaced in 1998 by the Winkel triple projection. But because of its balanced approach, the Robinson projection contains all of the distortions. But rather than having extreme distortions of any one type, like land size in Mercator or shape in Gall-Peters, the distortions are minimized, so they're less noticeable. So just to be clear, Robinson projections are more distorted than Mercator when it comes to direction, which Mercator prioritized at the expense of size. It is more distorted with size than the Gall-Peters because both Gall and Peters prioritized equal area at the expense of shape. But what the Robinson projection does, as well as the Winkel triple, it should be noted, is minimize distortion to present a more visually accurate representation of the Earth. That's the biggest positive of the Robinson. It looks accurate. On the negative, though, it has distortion of size, shape, distance, and direction. But it minimizes each of those to achieve the goal of creating a visually accurate projection of the Earth. That's where we'll leave off for tonight. Thank you guys so much, and I'll see you back in class.